Now we're going to focus on the effects of changing temperature and pressure and volume of a gas using Charles's law and Gay-Lussac's law. So Charles's law, let's look at a couple of demonstrations where volume and temperature are changing, but what's being held or constant is pressure. So in this demonstration, we have boiling water. They're going to place a balloon in the boiling water, and as you watch the balloon, you're going to notice that the gases inside begin to expand. The volume is increasing while the temperature is increasing. And the pressure is remaining constant because your container is flexible, and so the pressure is not a factor in this demonstration. Here's a similar demonstration, but opposite. This is liquid nitrogen, which is extremely cold, and when the balloon is placed in the liquid nitrogen, you can see that the gases are getting cooled down, which makes the volume decrease, and therefore the balloon is kind of collapsing inwards to decrease the volume. So Charles's law is volume and temperature when pressure is constant. This is a direct variation or proportion between the two things. So your formula is going to be the same formula as usual, but when there's a constant pressure, then that means the pressure is being ignored in the calculation, and so our equation would end up being V1 divided by T1 equals V2 divided by T2. Notice that if temperature goes up, so does volume. If temperature goes down, so does the volume. Direct relationship. So a Charles's law graph is going to be a straight diagonal line, because as volume is increasing, so is the temperature. So they both increase together. So now here's the equation, and Charles's law is going to be when pressure is constant, and so we ignore the pressure when we do the calculation with our equation. So it's a direct relationship. If temperature were to be increased times 2, then the volume is going to increase times 2. They're going to do the same thing together. So now let's practice some calculations. So here's our first example, and remember that our equation is P1 times V1 divided by T1 equals P2 V2 T2. So I'm going to label the variables I have in the problem first. If a 2-liter container, this is the first volume I've come to, so I'm going to call that V1. As I read, it's at 298 Kelvin. That's the first temperature I've come to, so we'll call that T1. And this is now my second volume, so we'll call that V2, and it has the same pressure. What is the temperature? So because what is the temperature is what I'm asked to find, I'm going to write T2, and I'm going to circle it, so I know that's what I'm trying to solve for, of the larger container. Because it's the same pressure, that means pressure is constant, and therefore we can ignore the pressure in our equation. So I'm just going to cut out pressure because pressure is constant. So now that we have our equation, it's going to be V1 divided by T1 equals V2 divided by T2. So V1 is 2.0 divided by T1 must be in Kelvin. It is already in Kelvin, so we can put T1 here at the bottom, and that's going to be equal to V2, which is 5.0 liters, divided by, and T2 is what I want to solve for, so I'm going to put an X right there. And now we're going to use our good old classic cross multiply. Remember, don't start your cross with the X. We'll do the cross opposite the X, and then whatever is left over is going to be divided by. So we're going to cross multiply opposite the X, 298 times 5, and then I'll just divide by that 2 in order to get the answer, 745. X equals 745. T2 will have the same unit as T1. Since T1 was in Kelvin, that means this answer is also in Kelvin. Sample problem number 2. Again, here is our equation. And as we read the problem, let's label the variables. If a sample of gas occupies 6.80 liters, that's the first volume I've come to, that's V1. At 325 degrees Celsius. Oh, when you see Celsius, you add 273. This is our first temperature, so we'll call that T1. So it's 325 plus 273 is my T1. What will its volume be? So what is my second volume? And then this is my second temperature, T2. You see how it's in Celsius? plus 273 automatically. Okay, so now let's go set up our problem. Remember, we have note that says pressure does not change, and they didn't give us any pressures, so that means that pressure is not a factor. So we'll just ignore that. So our equation is going to be V1 over T1, but I'm going to need to add my 325 plus 273, which is 598. So this is 598 equals V2 is my X over T2, and I'm going to have to add 25 plus 273, which is 298. So now that I have my problem set up, I can use cross multiplication to solve it. Remember to start your cross not at the X. So we're going to multiply these two numbers, and then the last number left we're going to divide by. 6.80 times 298 divided by 598 equals 3.39. So X equals 3.39. Whatever the unit of V1 is going to be the unit of V2. And V1 was in liters, and so that's how we know this is also in liters. Problem number 3. Again, here's our equation. Let's label our variables. Exactly 5.0 liters, that's my first volume, so I'll call that V1, of air at negative 50 degrees Celsius. That's my first temperature, and because it's in Celsius, add 273 to turn it into Kelvin. It is warmed to the second temperature, T2, of 105 degrees Celsius, add 273 to make it into Kelvin. What is the new volume? So V2, and I'm going to circle it so I know that's what I'm solving for. Notice that the pressure remains the same, so since they didn't give me any pressures, I can ignore it in my equation, and it's just going to be V1 divided by T1 equals V2 divided by T2. The fact that pressure is constant is how we know that this is Charles's law. All right, so let's set up our problem. It's going to be V1 over T1, but I need to add negative 50 plus 273, which will give me 223, equals, what is V2? So that's going to be my X, over, and then 105 plus 273 is going to equal 378. So now we can cross multiply to get our answer. Remember, don't start at the X, cross opposite the X. We'll do 5.0 times 378, and then we will divide by the thing that is across from the X. So divided by 223. So we have 8.48 or 8.5. And remember, whatever the unit was for V1, that's the unit for V2. V1 was in liters, so that means V2 is also in liters. Now you should pause the video and see if you can do this calculation on your own, and then unpause the video to watch the solution. So as usual, this is our equation. We're going to label our variables. A sample of carbon monoxide gas occupies 3.20 liters. That is my first volume. 125 degrees Celsius is the first temperature. If it's in Celsius, add 273 to change it to Kelvin. At what temperature? So what I'm solving for is T2. Will the gas occupy at 1.54 liters, that's V2, if the pressure remains constant? That means we can ignore pressure, and when you know pressure is constant, that's how we know that it is Charles's law. So now let's set up our calculation. It's going to be V1 over T1 equals V2 over T2. So we'll have 3.20 over, I have to add 125 plus 273, which is 398, to have my T1, equals, and then V2 is 1.54, and T2 is my X. So now I'm set up to cross multiply. So we'll do this times this, and then divided by that. 1.54 times 398 divided by 3.20, and we get 192. Now be careful, because the unit of T2 is the same as T1, but when we added 125 plus 273, we actually changed that temperature to Kelvin. So this answer is the temperature in Kelvin. And be very careful, if they wanted your final answer in Celsius, you'd have to subtract 273 from that to turn it into Celsius. But in this case, they didn't specify. So this law is called Gay-Lussac's law, and that is temperature and pressure when volume is being held constant. So when you see words like rigid container, that means that the volume can't change. It's like a steel container, or it's made of metal, or it's something that's not flexible like a balloon. So let's look at some demonstrations. So if you'll notice, they have the candles lit and the beaker is on top. So the air is being heated, which is making the pressure increase, pushing the water at the bottom. But as the candle goes out, now the air is cooling, the temperature is decreasing, so the pressure is also decreasing, which is what's causing the water level to rise inside of the beaker. Here's another example where this is a steel ball that has a gas inside of it, and so he's heating the gas. It's a rigid container, and then you can see on the pressure gauge that the pressure is rising as the temperature of the gas inside is increasing. Of course, if he heats it too far, then eventually there is a danger of the steel ball exploding, but of course he won't let it go that far. So Gay-Lussac's law is between pressure and temperature, and it's at a constant volume. The pressure of a fixed mass of gas varies directly, so these two things are direct with each other, which means as you decrease one, you decrease the other, or as you increase one, you increase the other. Here is the formula, and because it has a constant volume, that means we ignore the volume in the formula, and so that gives us P1 over T1 equals P2 over T2. So we'll do some calculations now. So now let's look at some Gay-Lussac's laws calculations, where, of course, we're going to use this equation, and let's label our variables in the problem. The gas in a used aerosol can is at a pressure of 1 atmosphere, so this is my P1. And it's at this temperature, that's going to be T1, remember, Celsius plus 273. If the can is thrown into a fire, what will be the pressure? So what will be the pressure? P2 is what I'm solving for. And then when the temperature reaches, so here's our T2, remember it's Celsius plus 273. So what you'll notice is we have two pressures, two temperatures. We have no volumes. So that means that volume is the constant in this problem, and that's how we know that it's a Gay-Lussac's law problem. So now I'm going to set up my equation. It's going to be P1 over T1 equals P2 over T2. And so my P1 is 1.00 over my T1 is 25 plus 273, which is 298, equals P2 is what I don't know, so I'm going to call that X, and then put it over, and this 928 plus 273 is going to be 1201 Kelvin. All right, so now I have my equation set up. I can calculate my answer, and I'm going to use cross multiplication. We don't start our cross at the x, we start opposite the x, so it's going to be this times this, and then divided by this. So we're going to do 1 times 1201 divided by 298, and that's going to give us 4.03, and so x equals 4.03. Remember, whatever P1 is, that's what my P2 is. P1 was atmospheres, so my P2 is also in atmospheres. In number 2, let's label our variables. A sample of nitrogen gas has a pressure of 6.58 atmospheres, that's my P1, at 539 Kelvin. Let me move my unit over here since it was on the next side of the page. So 539 Kelvin is my T1. I do not have to add 273 because it's already in Kelvin. If the volume does not change, so here we know volume is constant, what will be the pressure? So what will be P2? Circle it at 211 Kelvin. So that's going to be T2. So remember that our equation is P1V1 over T1 equals P2V2 over T2. And since volume is constant, that means that volume is not going to be a factor in our equation, and that's how we know that this is a Gay-Lussac's law calculation. So I'm going to go ahead and plug in my variables. It's going to be P1, which is 6.58, over T1, which is 539, equals P2 is what I don't know, so I'm going to call that X, over T2 is 211. Again, that was already in Kelvin, so I did not have to add 273. Now, I'm going to calculate my answer. You're going to start cross multiplying, not with your X, but opposite the X. So we're going to cross there, and then we'll divide by this number right here. So it's 6.58 times 211 divided by 539. That's going to get us 2.58. X equals 2.58. And then, of course, we found P2, so we'll go look at P1 to see that it is atmospheres. 3, I'll start by writing my equation. P1V1 over T1 equals P2V2 over T2. So now we'll go through and label our variables. The pressure in a car tire is 1.98 atmospheres. There's P1. At 27 degrees Celsius, there's T1, and Celsius means plus 273 in order to change it to Kelvin. After a long drive, the pressure is P2, 2.25 atmospheres. What is the temperature? So because it says what is the temperature, I'm trying to find T2. And then of the air in the tire. You'll notice that we were not given any volumes, and so that means volume is not a factor in this calculation, which is how we know this is a Gay-Lussac's law calculation. So now I'm going to plug in my variables. I'm going to put P1, 1.98, over T1. I've got to add 273 plus 27, which is going to give me 300 Kelvin, equals, put P2 over the T2. P2 is 2.25, and then T2 is my X. Notice that because we added 273 to this Celsius, the answer to that, which was 300, is our Kelvin temperature. So that means this is Kelvin, which means that whatever answer I get for X is also going to be in Kelvin. So let's go ahead and calculate this. You're going to start your cross, not with your X, opposite the X. So I'm going to cross multiply there, and then that leaves this, I'm going to divide by 1.98. So 300 times 2.25 divided by 1.98, and we get 341. So we're going to write X equals 341, and that unit is Kelvin. So with Gay-Lussac's law, let's consider how they're able to safely squeeze more gas into a large 18-wheeler tanker truck. So if you consider pressure and temperature have a direct correlation, then they can keep the temperature very low, which keeps the pressure very low inside of the tanker truck. How could it be dangerous to fill your tires on a very cold day? Well, when the temperature is low, the pressure is low, and so you could put more air in your tires than maybe you're supposed to. And then if you get the tires hot, then the temperature will increase, causing the pressure to increase, and so they could explode if actually you have a higher pressure than you're supposed to at that hot temperature.